atoms and elements. So in these notes, we're going to cover parts of an atom, average atomic mass, definite and multiple proportions, and a little bit of ions. So an atom is made up of protons, neutrons, and electrons in general. We have protons and neutrons here in the nucleus of an atom, and then around the outside we have electrons. This nucleus is very, very small compared to the size of the atom, which, since these are just a bunch of like electrons flying all different directions, that means the atom is made up of mostly empty space. From our periodic table, we can get a lot of information. We have the atomic number, which is here, and that is also the number of protons. We have the symbol for the element, usually the name is there, and then usually this, which is the average atomic mass. It is an average, which is why it's a decimal number. Now, you might ask, how did we get an average? Like, how do we know? Did we take all of the atom oxygens on the entire universe and add them, take all their masses, add them up, divide? No, that's not how we got an average, obviously. What we did is we made a standard. So we made carbon-12 the standard, just because it was so abundant, easily accessible, carbon-12. And we said that carbon has 6 protons, therefore it has 6 neutrons, giving it a mass of 12. You can't have half of a proton or half of a neutron. So given full numbers, it has a mass of 12, and therefore we have what we call our atomic mass unit, which are again whole numbers, and an atomic mass unit is basically a counting number. So 1 proton would be atomic mass unit of 1, 2 protons, atomic mass unit of 2, 2 protons and a neutron, atomic mass number of 3, and so forth. So again, the mass number is the protons plus neutrons. Again, that cannot be a decimal number. What you see on the periodic table is an average. The actual mass of an individual atom is based on the number of protons and neutrons. So here in boron 10, this 10 here represents, it's called hyphen notation, and this represents the mass number. In nuclear notation, it's up here. Again, that represents the mass number. In nuclear notation, we have this number down here, which represents the number of protons. In hyphen notation, we don't represent the number of protons. You can use a periodic table to see how many protons boron has by looking at the atomic number. So here we know boron has 5 protons, and if the mass number is 10, then that means we have 10 neutrons as well, right? If we need 5 plus something equals 10, 5 plus 5 equals 10. Here, boron still has 5 protons. Protons can't change, otherwise you change the element. So we're still in boron, which means we have 5 protons, but we have to equal 11 this time because our mass number is different. That means we have 6 neutrons in this one. So you can have the same number of protons and different numbers of neutrons. That's why our average of all the atoms in the whole universe is a decimal, is because some of those atoms, even though they're the same because they have the same number of protons, they have different numbers of neutrons. We call these isotopes. So isotopes mean that the same element, so here's the example we just saw, the same element, boron, has same number of protons but different numbers of neutrons. Almost every element has some sort of, has at least another isotope. Hydrogen has 3 isotopes. The mass of hydrogen, the average mass is 1.008. I mean, it's much longer than that, but let's go ahead and go with that. 1.008 is the average atomic mass. So the average of these 3. Well, the mass number of this one is 1, the mass number of this one is 2, and the mass number of this one is 3. So if they all exist in equal portions, our average would be closer to 2, not 1. That means this one must have a much higher percentage. Since it's really close to 1, that one must have 99%, and these two must make up the other 1% in order to get an average so close to 1. So in your assignments, you have a table that's bigger, but sort of looks like this. You can use the information given here to determine protons, neutrons, and electrons. So given here. So sulfur, in order to know the number of protons, I'd have to find it on the periodic table. Here's sulfur. It's kind of hard to read, but the atomic number is 16, which means I have 16 protons. Because this is an atom, I also have 16 electrons. And then to find my neutrons, I would do 32 minus 16 is 16. How did I know to use 32? That was the mass number. So my mass number here minus my neutrons equaled, or minus my protons equaled my number of neutrons. So I'm going to do that again for bromine. I'm going to find bromine on my periodic table, and here it is. So again, the number of protons is 35. That means my number of electrons is 35. And then to get my number of neutrons, I'm going to have to take 79, subtract 35 to get my number of neutrons, which gives me 44 neutrons. So if that's how we find the individual mass number, is adding up protons and neutrons, how do we find the average weight? So the weighted average just means that they're not split exactly. So if I have two isotopes, it's not 50% is one and 50% is the other. They have weighted averages. One might be 70%, which means the other one is 30%, because percents have to equal 100. If one of them is 10%, that means the other one is 90%, and so forth. So we can calculate that average atomic weight, the average atomic mass, what you see on the periodic table, by using information given like here. So it says boron is 19.9%, boron 10, which means a mass number of 10. So I'm just going to go ahead and put that in my formula here. So my mass number of 10, and that's 19.9%, but I'm going to divide that by 100, or move that decimal over 2 places and get 0.199. My other isotope is a mass number of 11, and again, I'm going to put that in its decimal format, so 0.801. Then I'm going to perform these calculations. So when I multiply that first one out, 0.199 times 10, I get 1.99. I want to have 3 sig figs because my 0.199 has 3 sig figs, and then the 10 doesn't count because it was a counting number, so that doesn't count for sig figs. Then I'm going to multiply together my 0.801 times 11. Again, the 11 is a counting unit, so that doesn't count for sig figs, so I want 3 sig figs in my answer, 8.81. So I'm going to add these two numbers together to get my average by multiplying it by the percent. I already gave it its weight, so now I'm adding it together to find the average. Whoops. When I add that together, I get 10.8, like in my calculator, but I want to make sure I put that 0 because I need 2 decimal places. Since I have 2 decimal places here and 2 here, I need 2 in my answer. So my answer is 10.8, and then I can write like grams per mole for average atomic mass. I could write AMU. There's a couple of units that work there. But you should be able to go on your periodic table and check and make sure that the average atomic mass is really close to what you got. So if I got something like 20 point something, obviously that's wrong and I made a mistake. But if mine says 10.81 or 80 and on your count or in your periodic table it says 10.81, that's okay. So here is another example, just worded a little bit differently, like in the format you might actually see it. So calcium has 2 primary isotopes, calcium 41, which comprises 8%, and calcium 40, which is the rest. So I'm going to take the mass, so 41, and I'm going to multiply that by the decimal of the percent, so 0.08. And remember, you are just dividing by 100 to get that, or moving the decimal place over. I have calcium with a mass of 40, and then percents are out of 100. So if one of them is 8%, I know the other one is 92%. So I'm going to put a 92. because there were 3 sig figs in this 8%, I'm going to go ahead and put a 0 there just to make 3 sig figs. That way I'm not changing anything. Actually, those two didn't count. I should have put 3 sig figs here as well. It doesn't matter math-wise, it just matters later for decimal places. So then I'm going to perform those and add them up. So because I'm switching rules, right? I'm doing a multiplication rule and then an addition rule, so I'm switching sig fig rules. I need to do these in 2 parts. So first I'm going to multiply the numbers together and get answers, and then I'll add them up, kind of like I did in the last one. So 41 times 0.08, I need 3 sig figs again because the 41 is a counting unit, so it doesn't count. So that's 3.28 with 3 sig figs plus, and then I'm going to multiply those two together, and I get 36.8. Again, I need 3 sig figs. So now I'm going to go ahead and add those two together. And in my calculator, I get 40.08. Here I have 2 decimal places, and here I have 1. So I need my answer rounded to 1. So that's going to give me 40.1. I like to write grams per mole. I think that's the most useful one. But for average atomic mass, again, you can write grams per mole, you can write AMU, either one. This is another way you might get the question where it's giving you the same information. I have silver with a mass of 107, but it's telling me that it has an actual individual mass, like a molar mass, and then here I have silver 109. Again, it's giving me like an actual mass, and then it's telling me that the average, so it gave me the number from the periodic table, it gave me the average, and it asked for relative abundance. So since I have the actual mass, that's what I'm going to use. So for silver 107, I'm going to use the mass of 106.905, and then I'm going to multiply that by its percent, but I don't have its percent. So when you don't have something in math, you use a variable, so I'm going to use x, and then plus the next mass, which was 108.904, and then times a percent. Well, I don't have 2 equations, so I can't really use y. I can't use a second variable, but I do have some information. So these are percents, right? X we know is a percent, and so this is also percent. So if this is 70%, we know this has to be 30%. If this is 10%, we know this has to be 90%. So how did we do that? Well, we took 100, we subtracted x to get the other percent. So that's exactly what we're going to do. But remember, when we put them into the equation, we divide it by 100. So 100 divided by 100, I'm going to say 1 minus x is going to give me that number there. So I'm just going to erase this real quick. Okay, so 1 minus x, and then it is all going to equal, remember it said the average atomic mass was 107.868. That looks like a comma. There we go. All right, so now I'm going to solve. So multiplying this through, that gives me 106.905x plus 108.904 minus 108.904x equals 107.868. So now I'm going to combine like terms by subtracting the 108.904 from both sides. And then I'm going to take my 106 with the x and my 108 with the x, and I'm going to subtract those as well because there's a subtraction sign here. And then I'm just going to rewrite it. So for my x, when I subtract those two, I get negative 1.9993 3 decimal places because I have 3 decimal places for each, and then x, which equals, and now I'm going to perform the other and get negative 1.036. Again, 3 decimal places. Then I'm going to divide, so divided by, to isolate my x, so I'm going to divide both sides by negative 1.99, which means x equals 0.518, and then it's 2, so I'm going to round it up to 3 because it's 2.5. So I'm going to round it up to 3 because I need 4 sig figs, right? I have 4 in both my numbers there, so I need 4 in my answer. Now remember, these are supposed to be a percentage. So if I multiply that by 100, it equals 51.83%. And what did I assign x to? I assigned x to this number here, which was the silver 107. So this was silver 107. So because percents are out of 100, if that's silver 107, then that means silver 109 equals 48.17%. Again, I got that by taking 100 and subtracting my 51.83. So that's how you find percent abundance. So it's going to ask you both ways. It's going to ask you this way to find the average atomic mass, and then it's going to ask you this way to find the relative abundance. All right, so if you want to stop here and do the worksheet for average atomic mass, you can do that. If you'd like to keep working or watching the notes, then do that. So moving on to law of definite proportions. So law of definite proportions basically means no matter how much you have, the ratio, like the percentage of elements within the compound, will stay the same. So an example that we use here is water. So water, if I have one molecule of water, like the oxygen and the hydrogen is 11% of the water, and the oxygen is the other like 88% of the water. I'm aware that that doesn't add to 100, but it's just because there's decimals in there. But if I have a drop of water, I still have 88% oxygen and 11% hydrogen. If I have a pool full of water, I still have 88% oxygen and 11% water. So that's all definite proportions means, is that no matter how much you have, the ratio of like hydrogen to oxygen still stays the same. So you might see something that says like if two samples, see here, if two samples contain hydrogen and oxygen, the sample A has 6 grams of hydrogen, 18 grams of oxygen, sample B has 1.5 and 12, are either or both samples water. So when I did the calculations for sample A, I got 25 and 75%. I know that that means it can't be water. It can't be the same ratio of hydrogen to oxygen, so I can tell that that's a different compound because it doesn't have the same ratio of hydrogen to oxygen. Sample B does. Therefore, I can tell that sample B is water. Law of multiple proportions says that compounds can have the same elements but combined in different ratios. So an example of that would be like water is H2O, and then hydrogen peroxide is H2O2. So you see that here as the examples, water and hydrogen peroxide. So the same elements, they both have hydrogen and oxygen, but they're combined in different ratios. In the water, hydrogen to oxygen is 2 to 1, whereas in the hydrogen peroxide, hydrogen to oxygen is 1 to 1. So in this example, I'm giving you two substances and asking you, are they the same? We use the same numbers as last time. We can see here that because these are the ratios of water to oxygen versus here, I can tell that they're different compounds, even though I know from the description that they have the same, they contain the same things. They both contain hydrogen and oxygen. They are different compounds because they have different ratios. That is the definition of law of multiple proportions. So everything you see on the periodic table is an atom. So what is an ion? An ion is when you change the number of electrons. So we saw it before in the first table that for an atom, protons and electrons are the same, but for an ion, that's not true. A cation is just a positive ion, and an anion is a negative ion. Sometimes you can remember that cation is positive because the plus sign kind of looks like a T, or anion. I've heard some people think that kind of is spelled like onion, and you don't like onions or they make you cry, so it's negative. I don't know, but however you want to remember it, cation is positive, anion is negative. For each, like for nonmetals, those are the ones that become anions. They are the ones that become negative. And in order to get a negative ion, you have to add on an extra electron. So here we can see that in our atom, we had 9 protons and 9 electrons, and here we had 9 protons and 10 electrons. That would make our fluorine an ion versus fluorine the neutral atom. Metals are positive, so instead of adding on an extra electron, here we're releasing an electron. So 11 protons and 10 electrons gives us a positive ion, versus the neutral atom, which was 11 and 11. Notice we never changed the protons. Here we have 11 and 11, and the electrons are what changed. Here we have 9 and 9, and the protons and the electrons are what changed. So the protons are always staying the same, the electrons are what is actually changing. And then these are the sort of like half reactions to show it. Again, notice I said that electrons are being released. That means they're on the products side of the reaction. And here I said electrons were being added. That's because they're on the reactants side. So you can see that here they're on the reactant side. So filling out like a similar table to what we saw before, if I had a chloride ion, so the symbol would be chlorine, I would have a 35. It has a -1 charge, and the atomic number is 17. So that means 17 protons. That means 18 neutrons, right? I would take the mass number minus, so 35 minus 17 to get 18. My electrons, if I have a -1 charge, that means I have one more electron than I do protons. So that means I have 18 electrons. The mass number is 35. How did I know that? It's right here. And then the average atomic mass I would look up from the periodic table, and I would see that it's 35.45. So you would just sort of do that for all of these if you on the table that kind of looks like this. But that's about it. If you have any questions, please email me or post to the discussion board.